Okay, so I'm going to be going over the Chapter 14 practice problems that you were given before break, and I will go through how to address each one of these. So starting with number 1, it says, what is the pH of a 0.15 molar solution of hypochlorous acid? You should realize that hypochlorous acid, HOCl, is a weak acid. We know this because it's not one of the strong. Therefore, double arrow upon dissociation, and it breaks down into H plus and OCl minus. So they want to know the pH, so that's one thing that we're finding, and they want to know the percent ionization. So let's address the pH first. So in our ICE table, we know that we're starting with a 0.15 molar solution, and we have initial concentration of 0. Our change is going to be minus x plus x plus x, 0.15 minus x, and x and x. And we need the Ka value for hypochlorous acid, so you could look that up in table 14.2. So the Ka is equal to 3.5 times 10 to the minus 8, and that's going to be equal to x squared over 0.15 minus x. And remember, I put this into my solver. I get x equal to 9.35 times 10 to the minus 5, and that's equal to the H plus concentration as well as the OCl minus concentration. So we want the pH, so pH is equal to negative log of the H concentration. So in this case, negative log of 9.35 times 10 to the minus 5 is going to give us a pH of 4.03. And then percent ionization is just like percent dissociation. It's going to be part over whole times 100. So the molarity, the H that dissociated was 9.35 times 10 to the minus 5 over 0.15 times 100, and believe you get 0.199, so just about 0.2% ionized, which should make sense because it's an extremely weak acid. You can tell that by looking at the very small Ka value, so I wouldn't expect that a lot would ionize. Let's move on to problem 2. What is the pH of a 0.25 molar C2H5NH3Cl solution? Well, what we have to realize here that this is a basic solution, so you basically have C2H5NH3 plus, because we're not interested in the Cl minus, and we're going to add that to water. I'll do it like HOH so you can see it. You don't have to write it that way. And that's going to give me C2H5NH4 and OH minus. So this is definitely a base problem. So let's set up our ICE table. We've got 0.25 molar initially, and these are going, we don't need to worry about the water. This is going to be 0, 0, minus x, 25 minus x, plus x, plus x, x, and x. So what's going on here, we need the Kb. I believe that was in table 14.3 for the C2H5NH3. Kb is equal to 5.6 times 10 to the minus 4. equal to x squared over 0.25 minus x. And when we solve for x, we get x equal to 0.12, which is equal to our OH minus concentration. It's also equal to the C2H5 and H4, but we're really not interested in that right now. We're only interested in the OH. And we know that the POH is equal to the negative log of the OH minus concentration. So therefore, the POH is equal to the negative log of 0.12, which is going to give us a POH equal to 1.9, and therefore 14 minus my POH is going to give me a pH equal to 12.1. So it certainly is basic. Okay. 3. What is the pH of a 0.15 molar solution of both nitric and nitrous acid? Again, you have to look at everything that is going to be in solution here. Nitric is a strong acid. Nitrous is a weak acid. The Ka of nitric is going to be greater than that of nitrous and water. So therefore, we're only interested in the nitric acid. It's the only one that's going to contribute the H to solution. So pH is simply equal to the negative log of 0.15. No real work to do here, and your pH is equal to 0.82. So you know that's a pretty strong acid. Okay, and the next one, we're dealing with a diprotic acid. Ascorbic acid is vitamin C. So you would have to look that up. It is in the book, and it has a formula of H2C6H6O6. If you recall, we did a long problem like this with phosphoric acid in the notes. So they want to know the pH and all concentrations of a species of 0.055 molar ascorbic acid. So in our first dissociation, we have C2C6H6O8, and it dissociates into H plus and HC6H6. This should be O6. Minus. And we know initially we have 0.055 molar, 0 minus x plus x plus x. 0.055 minus x, x, x. So we need to have two Ka values here. So Ka1, because this is the first reaction, step 1, is equal to 7.9 times 10 to the minus 5. You just have to look that up. And that's going to be equal to x squared over 0.055 minus x. And then I solve for x in my solver. X equal to 0.002, which is equal to the H plus concentration, and that's equal to the HC6H6O6 minus. So we're going to need this later. So I'm going to box it out in red so I can find it. Okay. We're starting with what we finished with. We have HC6H6O6 minus, and that dissociates into H plus and C6H6O6, 2 minus. Now remember, in this ice table, I'm starting with my concentrations that I just calculated. So this is going to be 0.002, This is 0.002. There's none of this yet. This is minus x plus x plus x. So this is going to be 0.002 minus x, and this is 0.002 plus x, and this is simply x. So my Ka2, when I look that up, I get 1.6 times 10 to the negative 12. You can see is extremely, extremely small. And that's going to be equal to 0.002 plus x times x over 0.002 minus x. And I put that all in my solver, and I get x equal to 1.59 times 10 to the minus 12, and that's equal to C6H6O6 2 minus. So that's going to be an answer. Now, a couple things going on here. Our H plus concentration is really 0.002 plus x in this problem right here, but x is so small that it's really not going to make a difference. It really isn't. So when we go back to our original, okay, they want the species of everything. Let's start. We got H2C6, H6O6. That's going to be equal to 0.055 minus x. And x in this case up here was 0.002. So that's equal to 0.055 minus 0.002, which is going to give us 0.053. So that's that one. Okay. Now you have, let's do the HC6, H6O6 minus. That's going to be equal to 0.002. We found that there. Then we also need C6H6O6 2 minus, which we just found out was 1.59 times 10 to the minus 12. And we know that H plus is equal to 0.002 from here, but then it's also equal to 0.002 plus x from here, but x is so small that it really is not going to make a difference if I add 1.59 times 10 to the minus 12 to it. For all purposes, it's going to be 0.002. And these are all molarities. And hopefully I didn't make any math mistakes. If I did, I'm sure you'll let me know about them. Okay, let's move on. So, next problem, we have to rank the following chemicals in order from lowest pH to highest pH. So let's do some work on this. Some of them are common sense, some of them we have to really analyze. So let's pick out what we know. We know that, KNO3 is a strong, K comes from a strong base, and the NO3 comes from a strong acid. So the K is coming from KOH, the NO3 is coming from HNO3, so this is going to be neutral. We know that KOH is a strong base. We know that H2SO4 is a strong acid. We know that HOCl is a weak acid. And we know that C2H5NH2 is a weak base. So we can do that without doing anything. Now, what we know here is that NaOCl The OCl minus comes from a weak acid, and the NaOH3 and the Na comes from NaOH, which is a strong base. So this is going to be, even though it's the salt of a weak acid, it's going to be slightly basic in solution. And the C2H5NH3 comes from a weak base, but the Cl comes from a strong acid. So even though it's a salt, it's going to be slightly acidic in solution. So now we have to do a little bit of looking at some Kas to figure out where exactly things fall into place. What do we know? Well, we know HOCl is 3.5 times 10 to the negative 8th. And we know that we can, this is table 14.2, and then 14.3, we know that this is 3.8 times 10 to the minus 10. Okay, we know this is a strong acid, we know this is a strong base, we know this is neutral, and now we have these ones in between. So the C2H5NH3 we have to figure out, using the Kb, what the Ka is. So remember, Ka would be Kw divided by Kb. So Ka is going to equal 1 times 10 to the negative 14 divided by, and the Kb, 5.6 times 10 to the negative 4, which is going to give me a Ka of NaOCl. So the Ka, we need the Ka for HOCl, but we have to work from, oh no, this is basic, I'm sorry. We need the Ka for HOCl, which is 3.5 times 10 to the negative 8. So we need the Kb here. So Kb is going to equal Kw divided by Ka, and that's going to equal 1 times 10 to the negative 14 divided by 3.5 times 10 to the negative 8th. So our Kb is 2.85 times 10 to the negative 7. So let's try to rank these. We're going from lowest pH to highest. So now we need to rank these pH. So we're going pH low to high. So H2SO4 is less than HOCl, which is going to be less than C2H5 and H3Cl, which is going to be less than KNO3, which is going to be less than NaOCl, which is going to be less than KOH. Okay. How do we rank these? Strongest to weakest. That's going to be HBrO3 is less than HBrO2, which is less than HBrO3. And these are oxyacids, and therefore more oxygen equals stronger acid. Okay, moving on. A water solution of which of the following compounds will turn blue litmus red? We're looking for a base. That should have been fairly easy. NaOH. Which represents a pair? Remember, pairs only differ by H plus. So that would be D. The following acids are listed in order of decreasing acid strength in water, according to Bronsted, Lowry, which one is the weakest base. Weakest base means strongest acid, so that would be I minus. Strong acid equals weak base. At 0 degrees, the ion product constant of water, Kw, is 1.2 times 10 to the negative 15th, so the pH is what? So you know that Kw is equal to H plus times OH minus. Therefore, 1.2 times 10 to the negative 15th is equal to x squared. Therefore, x is equal to, so x is equal to 3.46 times 10 to the negative 8. And we know that pH is equal to negative log of that. And you're going to get a pH equal to 7.46. When sodium oxide is added to water, what are the resulting products? Anytime a metal oxide is added to water, it yields a base. Just like anytime a non-metal oxide is added to water, it yields an acid. So we're going to get NaOH. And lastly, which of the following is the strongest Lewis acid? Remember which would be Al plus 3. I'm working on the recording for chapter 15. It'll be up by this evening.